So it is often said, and I think with some truth, that we don't understand what happened at the Big Bang, at the initial singularity, until we had a quantum theory of gravity. So I agree with that, and in fact I think I would even say more strongly than most people. I think that we act too much as if there was a Big Bang, which we really don't know because we don't know enough about quantum gravity. So I'm going to try to get some lessons for quantum gravity, even though we don't have yet the full theory, just from thinking more carefully about quantum mechanics itself. In particular, what I would call a wave function first viewpoint on quantum gravity. The idea here is to not take some classical theory of gravity like general relativity and quantize it, but just to look at quantum mechanics in its own right and see if something like gravity could pop out. So for those of you who are not experts in quantum mechanics, it's a completely different way of looking at the world than classical mechanics is. In classical mechanics, you have a particle that has a position and a velocity. That's an element of phase space, mathematically. And if you're Laplace's demon, then you tell me the position and velocity of everything in the world, I will predict what happens next and what did happen in the future. Quantum mechanics has a wholly different setup. It has something called the wave function. It's an element of a wholly different space called Hilbert space, the space of all quantum states, the space of all wave functions. And the property of the wave function, which might be a function of position, for example, is that it tells you the probability of observing the particle if you were to look at it. The way it tells you that is you take the wave function and you square it, and the wave function squared is the probability that the particle will be at that location in space. So, of course, there are conflicts and problems dealing with what we call interpretations of quantum mechanics. People don't agree on what quantum mechanics really is. I'm going to take a particular point of view. In particular, I'm going to give away my philosophical presuppositions by saying that it's the wave function that really exists. This is the sort of simplest, most natural interpretation of what quantum mechanics is trying to tell you. Every version of quantum mechanics has a wave function in it. And I'm going to say, well, that's trying to tell you that that's because what the world is. The world is represented mathematically by a wave function. But that is not what you observe. When you look at systems, you see them with positions or velocities or things like that. So the thing that makes quantum mechanics hard is that what the world is different than what you see when you look at the world. And this leads to this horrible mess, which is what we teach students, our second-year undergraduates, when we teach them quantum mechanics. We say, okay, there's a space of all possible quantum states. That's called Hilbert space. There's an equation that makes the quantum state evolve in time. And so far, so good. This is just like classical mechanics. There's a space of states, and there's an equation that makes them evolve in time. In classical mechanics, it would be Newton's equations or Hamilton's equations. In quantum mechanics, it's Schrödinger's equation. But then everything runs off the rails. You say that measurements return only certain values, not other values. These values are given to you probabilistically, and that after you make a measurement, the system is in a different state than it was when you started. And people start saying, well, what do you mean by a measurement? And other people say, nobody knows. So if you're confused by rules 3, 4, and 5, don't worry. So are the second-year undergraduates. So are 90% of the professors teaching the second-year undergraduate. So there is, in contrast with the textbook quantum mechanics method, there are other ways of approaching quantum mechanics. My favorite is the Everettian or many worlds quantum mechanics. And it starts off the same. It says there's a space of quantum states, and there is an equation telling you how the quantum states evolve through time. The difference between Everett and textbook quantum mechanics is that Everett stops there. He says that is it. There is no special set of assumptions or postulates dealing with measurement. He claims we can derive the apparent features of probability and wave function collapse, etc., just from these two ideas, the same two kinds of ideas that you had in classical mechanics. So I'm not going to go through all of the arguments for and against. This isn't the place to do that. Happy to chat about it over the typical beers. But I'm going to take the attitude that this is the right way to think about quantum mechanics and try to derive some implications of this idea. I think that the biggest implication is that this thing that we call the wave function, the quantum state, already on the previous slide I said the wave function is a function of position or a function of momentum or whatever. But that's not actually the way the theory itself works. The theory itself is a theory of wave functions. It's It's a theory of quantum states. To say that the quantum state is a state of something, of position or of momentum, is a very human thing to do. We human beings treat the world as classical in our way of intuiting things, and therefore we always start with a classical theory and then quantize it. Nature doesn't do that. God doesn't do that, I think Lemaitre would say. Nature is quantum mechanical right from the start. And in fact, we have explicit examples. This is a fancy one, the ADS-CFT correspondence, but there's much more down-to-earth examples. Examples where there is a single quantum mechanical theory that can be interpreted in more than one classical way. In the case of ADS-CFT, there is a single quantum mechanical model which can be thought of as either quantum field theory in four-dimensional flat space-time without gravity, or as quantum gravity in a five-dimensional negatively curved cosmological space-time. The same exact quantum theory with two different classical ways of talking about it. So if you want to say, which theory is it really? My answer is, it's the single quantum theory. These two different classical ways of looking at it are just conveniences that might be useful to us in certain circumstances, but not in others. So that introduces a new problem into quantum mechanics, if you take that point of view. If you just gave me a quantum state and some evolution equation, which classical reality does it actually refer to? What is the classical reality? What is the world? What is the space? What is space-time, etc.? So this is what I will call wave function first quantum mechanics. Rather than thinking of the quantum state as a state of something that gives me some probabilities for seeing what reality actually is, just take the wave function itself seriously as a vector in Hilbert space and try to extract all of our classical realities from that. What that means is that things like space and perhaps time is a whole other thing worthy of a whole lecture in and of itself, but space, fields, particles, all the ordinary furniture of physics should emerge from this quantum mechanical state. They should not be put in by hand to start. The idea that wave functions collapse is just an artifact of our observations in the particular world we're in. In ever-ending quantum mechanics, wave functions never collapse. There's a process called decoherence, which I'll talk about in a second. And the last little footnote is that how big Hilbert space is, the number of dimensions that it has, is critical. This is not dimensions in the sense of dimensions of space where we have three dimensions of space. This is, Hilbert space is a vector space, and every vector space is characterized by its dimensionality. The dimensionality of Hilbert space is really, really big. The dimensionality of Hilbert space for a hydrogen atom is infinity, okay? We don't know if there are really an infinite number of dimensions of Hilbert space or only a finite number. That will be crucial. So for example, it is crucial for the question that we started with, did the universe have a beginning? Is the Big Bang the beginning of the universe? The answer is we don't know, but there's a sort of four-box possibility. One dimension is the dimensionality of Hilbert space finite or infinite? The other is the Schrödinger equation that lets the universe evolve with time really the fundamental equation of reality? Or does the real function, the real quantum state of the universe not evolve at all? Is it completely static? This is a version of what is called the Wheeler-DeWitt equation. So every four of these boxes is empirically allowed according to the current state of the art. We don't know which one is right. Many people, including our organizer, Thomas, and Stephen Hawking, Jim Hartle, have spent a lot of time working in this box, where the dimensionality of Hilbert space is infinite and the universe does not truly evolve. In that case, time is emergent. Time is not fundamental. Time is just a useful approximation. The universe in different models may or may not have had a beginning. In other models where the dimensionality of Hilbert space is finite and time is emergent, the universe definitely did have a beginning. Whereas if the dimensionality of Hilbert space is big and time is fundamental, then the universe is necessarily eternal. It can go on forever, and the Big Bang is just a phase through which the universe passed. So quantum mechanics is not enough yet to tell us whether or not the Big Bang truly is the beginning. All right, let's think about something more down to earth. Schrödinger's cat, which you have to hear about and talk about quantum mechanics. You've heard probably the basic setup. There's something quantum mechanical that smashes a hammer into a vial of poison, and then the cat goes into a superposition of being a I think my father just didn't like cats. So that's why Erwin Schrödinger liked to kill the cat. So the point of this is that if you believed in classical mechanics, you might believe that in the box there was a cat that was either awake or asleep, but you don't know. So you therefore describe it probabilistically. Quantum mechanics says that there really is the possibility that inside the box there is both. The real cat is in a superposition of awake or asleep. And this leads us into stretching our quantum mechanical intuition a little bit. The classical intuition says that, look, if you believe in classical mechanics, it's fine. You believe that there are cats that are awake, there are cats that are asleep. Quantum mechanics is weird because quantum mechanics says that you can be in superposition, and I don't really like that. That is how almost every human being alive on Earth today thinks. If you have truly quantum intuition, then the idea that cats are in superpositions makes perfect sense to you. I'm not going to claim to have perfect quantum intuition myself, but if one did, that's what it would be like. The weird thing is that when you open boxes, you never see cats in superpositions of being awake and asleep. When you open boxes, you only ever see them either awake or asleep, but not in superpositions. That's what Schrödinger's thought experiment challenges you to think about. And the answer will be in what we call decoherence. So here is the story you would be told about Schrödinger's cat were you to be that second-year student taking quantum mechanics for the first time. This is the textbook version of it. And in the textbook version, this is Professor Heisenberg, who is responsible for the Copenhagen interpretation, which is partly is closely related to what I'm calling the textbook interpretation. In that interpretation, you treat the observer as something special and classical, not part of the intrinsic quantum mechanical description. The cat is quantum mechanical. The cat is really just, in my examples, just a trick to be a two-state system, an electron that could be spinning clockwise or counterclockwise. But the cat is a quantum mechanical system in a superposition, curly brackets. The classical observer is in square brackets, and that's defined by the rules of classical mechanics. So in the textbook thing, what happens is when the observer looks at the cat, the wave function collapses. It goes stochastically and unpredictably into some probability the cat was awake and the observer saw it awake, some probability the cat is asleep and the observer saw it asleep. This is the usual way we are taught quantum mechanics. In Everett, or many worlds, here is Professor Everett, who naturally left physics after his theory of quantum mechanics got a very bad reception among other people thinking about it. This is what happens to people who think this way in this field. But he did write a PhD thesis before leaving physics, and his PhD thesis gave us this theory that says everything is quantum mechanical. There's no separation between the classical world and the quantum world, so everything is in curved brackets here. And what happens is there's just an ordinary interaction between the observer and the system. So you just measure it. You just look at it, you interact with it physically, and what happens is you become entangled. This is the very common phenomenon of quantum mechanics. When two quantum systems interact, they become entangled. So the universe evolves smoothly and deterministically under the Schrödinger equation to a superposition of cat is awake and you saw it awake, plus cat is asleep and you saw it asleep. So really the question is not, why do you never see a cat in a superposition of awake or asleep? The question is really, why don't you ever feel like you are in a superposition of seeing one cat versus seeing the other? And decoherence is the answer. Decoherence says you have to add to the quantum system the environment, which is just everything else in the world, because in quantum mechanics, individual pieces of the world don't have separate states. There's just one big state for the universe. And what happens is, once again, measurement. The observer looks at the system. The observer becomes entangled. Decoherence is the step where the observer and the system become entangled with the environment. That happens very, very rapidly, way before you can even think about it. And therefore, what happens is the whole wave function of reality becomes awake cat, person saw the awake cat, environment is entangled with that, plus the same thing for the asleep cat. The reason why that environment step is important here is because now the environment in this branch of the wave function and this branch of the wave function are orthogonal to each other as vectors, which means that nothing that happens in this part of the wave function will ever interfere quantum mechanically with what happens in this part. In yet other words, these two branches of the wave functions will evolve in the future as if the other one doesn't exist.
They evolve as if they are separate, independent worlds, which is why this is called the many worlds interpretation of quantum mechanics. But notice that I didn't put any worlds in. It's all just Hilbert space. Hilbert space is the same size in the Everett interpretation as in the textbook interpretation. I'm just using it. Every interpretation of quantum mechanics that is not Everett should be called the disappearing worlds interpretation, because their whole job is getting rid of the worlds that are there in Hilbert space. All right, that was the comprehensible part. Now I will try to tell you why this is important for cosmology. Remember, the universe is accelerating. I'm showing data in my talk. It's good to show at least a little bit of data in every talk, no matter how abstract. Here is a photograph I took in my laboratory of dark energy. It is a false color photograph in the best NASA tradition. Dark energy in this context, it's just Einstein's cosmological constant. It's just a constant energy density in every cubic centimeter of space. 10 to the minus 8 ergs is the measured value, and it makes the universe accelerate. And that leads to a problem called the Boltzmann brane problem, which I will try to tell you almost completely goes away if you think correctly quantum mechanically. So here's why there is a Boltzmann brane problem. So here's you and your friend in the universe. You're very far apart. Let's say you're 20 billion light years apart from each other. If you have vacuum energy, the universe expands forever at the same rate. And what that means is that around you there's a horizon. So if your friend is further away from you than the horizon, no light signal can ever get from you to your friend, because the space in between expands faster than it would take. So essentially, classically sort of pre-relativistic language would say your friend is moving away from you faster than the speed of light. Nothing's really moving faster than the speed of light, but that's effectively what is happening. There's a theorem, the cosmic no-hair theorem, that says that as this happens, as the universe expands and accelerates, all the lumpiness of the universe goes away. The eventual future state of the universe is just empty space with nothing in it but vacuum energy. And that state, as Hawking and Gibbons told us, has a temperature. The temperature of the real world will be a very low number, 10 to the minus 30 Kelvin, as opposed to the 2.7 Kelvin it is now. But it's still not zero. Even empty space has a temperature, says the conventional theory, the correct theory of quantum mechanics in de Sitter space. So there's a prediction that when you have a temperature, you're just like, imagine you're in a box of gas with a non-zero temperature, there are thermal fluctuations. This is a plot of the entropy in a box of gas that is mostly in equilibrium. There's tiny fluctuations downward in entropy, as Boltzmann taught us a long time ago. So if you have an eternal universe with thermal fluctuations, there will be occasional times when a couple of photons come together and make an electron-positron pair. There'll be a couple times when a lot of photons come together and make a few atoms and anti-atoms. There will be even times when particles come together, just thermal fluctuations, and make people, or planets, or galaxies, or the universe. So if you ask yourself, what are most observers in this kind of universe going to look like? They will be the minimal kinds of fluctuations that you need to make an observer, an intelligent being. Roughly speaking, that means you make enough fluctuation to make a little brain that looks around and says, thermal equilibrium, and then it dies. So this cosmology seems to make a strong prediction that almost all observers should be these ephemeral Boltzmann brains. This is a picture from the New York Times. It's mislabeled. This is not Boltzmann's brain. Boltzmann's brain is underneath a gravestone in Vienna. This is a Boltzmann brain that fluctuated into existence from nothing. And notice I didn't talk about inflation or the string theory landscape or the multiverse. This is the best fit cosmology that all professional cosmologists believe in. Our universe will expand forever, last forever. There should be an infinite number of these Boltzmann brains popping into existence. Except that they won't, because that is a wrong way to think about quantum mechanics. What you actually have calculated, and what the people who believe in the Boltzmann brane problem calculated, is not the probability that a Boltzmann brane pops into existence, but the probability that were you to be in that quantum state with a Boltzmann brane detection apparatus, what is the probability you would detect a brane in the quantum vacuum? But there is no one making measurements. There's no wave functions collapsing here. This whole process of decoherence that I told you about relies on the fact that our universe is very, very far from equilibrium. It has an arrow of time The decoherence happens only toward the future, not toward the past, because the past, there's less and less entanglement, lower and lower entropy. In thermal equilibrium, you're done with that. There is no more arrow of time. You're in a stationary quantum state. There is no fluctuating into anything at all. There's no particles popping in and out of existence. There's no brains or planets or universes popping in and out of existence. This is a reconstructed image of an actual wave function of an electron in an atom. It can just sit there. The idea of a quantum fluctuation is the idea that were you to look at that wave function over and over again, you would get different answers for the question, where is the particle? But if you're not looking at it, it's not moving, this particular wave function. Likewise, the vacuum of the quantum field theories of the universe in the ultimate de Sitter space. So there's going to be nothing fluctuating in and out of existence. The Boltzmann brane problem is actually much more rare than you might have been led to believe. Okay, with my minus 1 minute left, oh no, I have time left, right? I have half an hour, yeah? Okay, I have 8 minutes left. So, good. I want to tell you about, this was a, so what I told you about so far was more or less conventional stuff that I think I understand. In my last couple of minutes, I want to tell you about something that nobody understands, but is very, very provocative. Remember, I said at the beginning, if in this wave function first viewpoint on cosmology, rather than taking some classical system and quantizing it, we work right with the quantum mechanical system and ask what emerges. There's a huge problem with that in that it seems highly underdetermined. This is what is called the set selection problem. Given a wave function of the universe, there are many, many ways to divide it into subsystems and ask what the subsystems look like from one point of view or another. This is an ongoing research problem that I don't know the answer to. I have some ideas. Stay tuned. We think that we're on the right track, but that's not yet solved. Let me assume that it is solved. This is the biggest, I think, unanswered problem. And all of this is sort of stuff that could have been tackled in the 50s and 60s, but people were too busy finding new particles to really bother about it. So this is the fundamental quantum mechanics of a system that can be divided up into many little subsystems, many little quantum degrees of freedom, okay? But I'm not telling you what they are, where they are, or anything like that. I'm just giving you a quantum state corresponding to all these different little subsystems. So in a specific quantum state, what I can do is I can measure the amount of entanglement between different little subsystems. That's one thing I can do. Another thing is I can draw a region around any set of subsystems and ask what is the entropy of that region. In fact, the entropy is a measurement of the entanglement. The more things are entangled across these boundaries that I've cut with my region, the higher the entanglement is. Entropy and entanglement go together. If there's no entanglement whatsoever, the entropy of this region will be 0. So that lets me define something called the mutual information between two regions or two subsets. You think about it, this looks like a weird formula, but it's actually not that weird. This says, let's say you take this one, what is this called, H17 and H4, two different subsets of Hilbert space, two different little degrees of quantum freedom, okay? When I say SA plus SB minus SAB, what I mean is, what is the entropy of this? That's asking how much is this little subset entangled with everything else, plus the entropy of this, how much is this entangled with everything else, minus the entropy of the two of them together. So if I subtract off the entropy of the two of them together, what I'm really asking is how much entanglement is there just between those two, not between those two and the rest of the world. I call that the mutual information because that's what it is. It's telling me if I knew what was happening in one subsystem, what would that tell me about what's happening in the other subsystem? Now we know it is a feature of the quantum vacuum in systems that we understand that regions that are close together have a high degree of mutual information. They are highly entangled, highly correlated with each other. And as you get further and further away, the entanglement between regions goes down and becomes less and less. That is a true fact that we know. In this idea, which is called emergent space from quantum entanglement, we reverse that relationship. We say we have no idea what distances are because we didn't mention distance. Distance isn't in Hilbert space. Distance is in your old-fashioned classical way of looking at the universe. All we have in Hilbert space are wave functions, entanglement, things like that. So let's define the distance to be such that when regions are highly entangled, they're close together. When regions are very far away, when regions are unentangled, they're very far away. So what that does is it puts a graph on our set of subspaces. Our little subfactors, our degrees of freedom, are now connected by edges, and each one of them is weighted by this distance, and then we can do math on it. We can ask questions like, does this fit together to make a nice geometry with a certain number of dimensions and so forth? This is a classical kind of math problem, which means that it was sort of done in the 70s, and you can take a graph like this and plug it in. Here, what we did is just to check that we weren't making a mistake, we took a quantum system defined in 2 spatial dimensions. We forgot that it was defined in 2 spatial dimensions, but we calculated all these mutual informations, and we plugged it back into our algorithm, and we got back, yes, it lies in 2 spatial dimensions. So this is just a set of assertions. We didn't sort of prove that anything works here. What we're saying is, imagine that distances in space are defined by quantum entanglement. Can we use that to describe a smooth manifold? The answer is yes. Where it becomes interesting is when you say, okay, well now perturb that state a little bit. You have a state that starts just flat space, and I haven't introduced time yet, okay? So it's really just space. I have flat space. It has a certain entanglement structure, but now I tweak the state a little bit. I poke it. I perturb it in some direction. What happens? Well, if I change the state, I will change the amount of entanglement around it, so I will change the induced spatial geometry in a way that is very well defined. Roughly speaking, the graph is on here. Roughly speaking, if I change the amount of entanglement to be less, then that point moves away from everywhere else. Okay, so this is the geometry that you would get by decreasing the entanglement between this point and everywhere else. Now, what you would like to do is say, okay, can that change in geometry be related to energy? That's what Einstein did in general relativity, right? But there's no such thing as energy, just like there's no such thing as space. I need to define what I mean by energy. It turns out that when I have a statistically mixed quantum state, which I will for any region of space that has non-zero entropy, I describe it not by a wave function, but by something called a density matrix. And every density matrix, you can take the logarithm of it to get something called the modular energy. It's a complicated thing I won't go into. The modular energy is what the energy would be if this state were thermal. Okay, there you go. So it turns out when you change the quantum state, you change the density matrix, you change both the entropy of the region you're looking at, and you change the modular energy, and there's a law, the entanglement first law, that says the change in entropy is proportional to the change in energy, the change in modular energy. So all this stuff is known. It's fairly recent, but it is well known to people working in the field. What we showed is that in our approach, where we defined the geometry using quantum entanglement, there's a relationship between the spatial curvature induced at a point and the modular energy. They are exactly proportional to each other. It's not the most surprising thing in the world. What else would it be? At linear order, we're doing perturbation theory. But if you imagine that there's a limit of long distances, where you look far away and there's many, many quantum degrees of freedom, there is a belief, and there's many, many steps you can see here are sort of taking on faith, but there's a belief that in the infrared limit of large distances, where you ignore massive particles and everything, the world looks like what is called a conformal field theory. A field theory with no mass scales, because you're looking at a distance larger than all the mass scales. And it turns out that in conformal field theories, there is a relationship between the modular energy and the usual energy momentum tensor. Namely, the modular energy is proportional to the energy density of the conformal field theory. And therefore, we have a relationship between spatial curvature and energy density. We only have it in space, we don't have it in space-time, but there is a unique four-dimensional covariant equation which would reduce to this equation in the right limit, namely Einstein's tensor is proportional to the energy momentum tensor, namely Einstein's equation of general relativity. So what we're suggesting, and it's just an aspiration, a hope right now, it's not a derivation of anything, what we're suggesting is, instead of putting in a theory of geometry like Einstein does, and then trying to quantize it and getting all the difficulties that quantum gravity gets, if you define geometry by using intrinsically quantum mechanical notions like entanglement, then that geometry is going to automatically be dynamical. Of course it will, because the entanglement will change as the quantum state changes from place to place. And the simplest and most robust equation for that emergent geometry to obey is actually Einstein's equation. So it might be that the right thing to do is not to quantize gravity, but to find gravity within the emergent space-time of quantum mechanics. So we need to do a lot more. But this is what I just said. Geometry is automatically dynamical. It obeys Einstein's equation. The one little footnote that I didn't emphasize here, but it's important, is that the Hilbert spaces I was looking at are actually finite dimensional. There's an argument that that's what you should look at. There's also arguments that's not what you should look at. So this is one of the big open questions in this game. But it might turn out, I just want to leave you on the optimistic conclusion, it might turn out Hilbert space is locally finite dimensional, geometry is dynamical and comes out automatically, and quantum gravity turns out to be one of the simplest consequences of taking quantum mechanics seriously. Thank you.
Thank you very much, Sean. Thomas.
I was wondering, did anybody try to, instead of getting geometry from quantum mechanics, to do the first step? I would say it's getting topology from quantum mechanics, and maybe like EPR equal ER, or X in the quantum space, foam, conjectural wheeler, something like this.
Yes, yes. So you kind of need geometry first, even in ER equals EPR. So just for those of you who are not experts, which is maybe most of you, 1935, Einstein and Rosen wrote two famous papers. One was the Einstein-Rosen bridge, the first wormhole, the wormhole that connects the eternal black holes in the Schwarzschild solution. And they teamed up with Podolsky to write the EPR paper about quantum entanglement. None of these people thought these two papers had anything to do with each other. But more recently, Maldacena and Susskind have suggested that in fact they do, from this exact kind of reasoning. If you change the entanglement structure, then you change the geometry of space. So here I do what happens when I decrease the entanglement between this degree of freedom and its neighbor. So what if I also increase the entanglement between this degree of freedom and something very far away? So they said, well, in that case, it would be like having a microscopic quantum wormhole that connects these two very, very distant particles. Many people rolled their eyes, but they have certain examples in the context of the ADS-CFT correspondence where this seems to really happen. This is part of what inspired us. These microscopic quantum wormholes are probably not traversable. Otherwise, you could send information faster than light in the background classical space-time. It's not even clear what it means to say you have a microscopic quantum wormhole. It's not classically geometric in any ordinary sense. But as we probe more deeply into what it means to say that geometry comes from entanglement, that's the kind of stuff we're going to need to work out.
Well, it's topology, it's a handle in space, right? You could characterize it by an integer number.
You could, that's right, except that only if you believe it either exists or doesn't. If you believe that it has a sort of scale of existing, then it's a little bit harder.
So you showed us before this kind of quadrant of four variants of quantum mechanics.
Yes.
And their proponents, the workers there. Is there any hope that, other than simply a sort of aesthetic preference, are these things potentially falsifiable?
Well, they're testable.
What?
They're testable in the sense that the real problem here is not that we haven't tested them, is that they don't exist, these theories. These theories just haven't been developed to the extent where we can make the right predictions. But people like Thomas have worked very hard on connecting quantum cosmology to inflation, and therefore predictions of that. Joe talked about the need for a theory of initial conditions for perturbations. That's the kind of thing you would like to pop out of this if it really made sense.
I would like to ask something that was not clear. You were talking about the spatial structure, but I think you mentioned something related with the causality. Because where the causal structure will emerge here?
Yeah. Right now it doesn't.
Yeah,
there is that is definitely a problem. Yes, yeah, that's right. As with every single unfilled in step in the program, there are reasons to be optimistic that there it is filled in. It can be filled in. There's something called Lieb-Robinson bounds. Have you heard this phrase? So if you have a finite dimensional quantum system and you have a Hamiltonian, it very naturally has light cones all by itself. It is easy to get a causal structure. What's hard to get is a Lorentz invariant causal structure, because dynamically, if you have different kinds of degrees of freedom, generically they would have different light cones. You would not have a Lorentz invariant theory. So the aspiration would be a renormalization group flow to a Lorentz invariant fixed point in the infrared. That is to say, things are not Lorentz invariant nearby, but as you get bigger and bigger, they become more and more Lorentz invariant. No one knows how to make this happen right now.
So you are thinking about the Euclidean structure there?
Right now, we're just Euclidean. We have hopes.
Okay. Last question. If you have parameterized states in Hilbert space, you have this Fubini study, Fubini metric.
Metric, yeah.
This metric, was the connection of that with what you have just
Oh,
defined?
not that much. So the point is there is a metric in Hilbert space itself that is really just not very helpful for this kind of thing. What we really need, we need this dynamics. We need to be able to say what distance really is how far things move in time, right? And so since we don't have time evolution yet, we can't actually say that what we've defined as distance is what you and I think of as distance. But it's not the Hilbert space metric.
In the case of the wave function of the universe,
I get it.
do you really need a Hilbert space?
Well, good.
The
If
universe just as one single state.
so, people like you think that because you think you believe in the Wheeler-DeWitt equation. But so the Wheeler-DeWitt equation says h psi equals 0, and psi does not evolve. Psi is the quantum state. And in that case, you're right. You don't really need Hilbert space. It's just one state for the universe. I'm agnostic about whether or not the universe actually works that way.
Good. Yeah, how very good. Does the measurement make a difference in the definition of the distance?
Well, good. You want it to be robust. So there's a discourse to be gone through about classicality and non-demolition of things. So the fact that we are so very far from equilibrium gives us an emergent classical limit, gives us a regime in which you can measure things with meter sticks and clocks and so forth. In the real world, you can measure things without really doing a quantum measurement, right? And what that means is that we live in the special states of our subfactor of Hilbert space that are robust to being monitored by their environment.
Certain stability.
Yeah.
Thank you.